Hello and welcome to today's session. Today, we're diving into a key concept in computer science called a stack, which is a fundamental data structure used in algorithms and programming. If this is your first time hearing about stacks, or if it sounds complex, don't worry. We'll start from the very basics and build up step by step. A stack is a simple way to organize data with a specific rule that makes it powerful for solving certain problems. We'll use a real-life analogy to make it relatable, explore a practical problem with a visualizer to see it in action, and discuss how efficient it is in terms of time and space. By the end, you'll feel confident understanding and using stacks. Let's get started. Understanding what a stack is. Let's begin with the core idea of a stack. A stack is a data structure that stores a collection of items, like a list, but it follows a strict rule for adding and removing items. This rule is called last in, first out, or LIFO, spelled LIFO for short. This means the last item you add to the stack is the first one you can remove, and you can only add or remove items from the top of the stack. You can't access items in the middle or bottom without removing the ones above them first. Think of a stack as a vertical pile where you place items one on top of another. The top item is the most accessible, and all operations happen at the top. The main operations are push, which adds an item to the top, and pop, which removes the top item and returns it. There's also peek, which lets you look at the top item without removing it, and is empty, which checks if the stack is empty. Stacks are useful because their last in, first out rule makes them perfect for problems where you need to process items in the reverse order of how they were added, like undoing actions or tracking steps in an algorithm. Despite its simplicity, this structure is a powerful tool in many scenarios. Real-world analogy: a stack of plates. To make this concept come alive, imagine a stack of plates in a kitchen or cafeteria. When you have clean plates to store, you place a new plate on top of the pile. When you need a plate for serving food, you take the topmost plate off the pile. You can't pull a plate from the middle or bottom without removing the ones above, as that would risk toppling the stack. This is exactly how a stack data structure works. Adding a plate is like the push operation, placing a new item on top. Taking a plate is like the pop operation, removing the top item. If you want to check the top plate without taking it, that's like peek. If there are no plates left, the stack is empty, which is empty would confirm. The last in, first out rule is natural here. The last plate you stacked is the first one you use. This analogy helps us see why stacks are ideal for managing items where the most recent one needs to be handled first, like keeping track of tasks or steps in a process. Why stacks are important in algorithms. Stacks are widely used in algorithms because they provide a disciplined way to manage data. They're perfect for scenarios where you need to reverse the order of operations or temporarily store items. For example, in a web browser, the back button uses a stack to store the history of visited pages, so clicking back takes you to the most recent page first. In programming, stacks manage function calls, remembering where to return after a function finishes. They're also key in problems like checking if parentheses in an expression are balanced or evaluating mathematical expressions. The strength of a stack lies in its simplicity and restriction to top-only operations. This makes it easier to solve problems that involve tracking or reversing sequences, as you don't need to worry about accessing or rearranging items in the middle. Stack operations. Let's explore the core operations of a stack, as these are the tools you'll use to work with it. The push operation adds an item to the top of the stack. When you push an item, it becomes the new top, and all previous items shift down one level in the stack, still accessible, but only after removing the items above. The pop operation removes the top item from the stack and returns it. After popping, the item below becomes the new top. If the stack is empty, trying to pop typically indicates an error or returns nothing, depending on the implementation. The peek operation lets you view the top item without removing it. This is useful when you need to check what's on top before deciding whether to pop or push. The isEmpty operation checks if the stack has any items. This helps prevent errors, like attempting to pop from an empty stack. These operations follow the last in, first out rule, ensuring that the most recently added item is always the one you interact with next. Together, they make the stack a versatile and efficient structure for specific tasks. Problem statement: validating parentheses. To see a stack in action, Let's tackle a classic problem where stacks are incredibly useful: validating a sequence of parentheses. The problem is to determine if a string of parentheses, such as this string, is valid. A string is valid if every opening parenthesis has a matching closing parenthesis in the correct order and all parentheses are properly paired. For example, this string is valid because each opening parenthesis is matched by a closing one in the right order, forming nested pairs. However, this string is invalid because an opening parenthesis lacks a match, and this string also is invalid because a closing parenthesis appears before an opening one. Our task is to check if this string is valid. We'll use a stack to solve this by pushing each opening parenthesis onto the stack and popping to match closing parentheses. If the stack is empty at the end and all matches are correct, the string is valid. This problem is perfect for a stack because the last in, first out order naturally handles nested pairs, ensuring that the most recent opening parenthesis is matched first. Let's solve the parentheses validation problem for the string open parenthesis, close parenthesis using a stack. Start at index 0, where the character is an opening parenthesis. Since it's an opening parenthesis, push it onto the stack. Move to index 1, another opening parenthesis. Push it onto the stack. At index 2, the character is a closing parenthesis. For a closing parenthesis, check if the stack is empty or if the top item is a matching opening parenthesis. The stack is an empty, and the top item is open parenthesis, which matches. Pop the top item. At index 3, another closing parenthesis. The stack has one open parenthesis at the top, which matches. Pop it. After processing all characters, check if the stack is empty. Since the stack is empty, all parentheses were matched correctly, confirming the string is valid. Time and space complexity of stack operations. Let's examine why stacks are efficient by looking at their time and space complexity, which tell us how fast operations are and how much memory is used. For time complexity, all stack operations are extremely fast because they only involve the top of the stack. The push operation adds an item to the top, which takes a single step, regardless of how many items are in the stack. This is called constant time, or big O of one time. The pop operation removes the top item, also in one step, so it's constant time as well. The peek operation simply looks at the top item without modifying the stack, taking one step, making it constant time. The isEmpty operation checks if the stack has any items, typically by checking the stack size, which is a single step, so it's also constant time. This constant time efficiency makes stacks ideal for applications where you need quick access to the most recent item, as the number of items in the stack doesn't affect the speed of these operations. For space complexity, the stack needs memory to store its items. If the stack has n items, it uses space proportional to n. This is called linear space, or big O of n space. For example, if you push 10 items, the stack uses space for those 10 items. If the stack is empty, it uses minimal space, but the maximum space depends on the number of items stored. In the parentheses validation problem, the space complexity is big O of n in the worst case, where n is the length of the string. If the string is all opening parentheses, like open parenthesis, open parenthesis, open parenthesis, open parenthesis, the stack stores all in characters. The time complexity for the algorithm is big O of n, as you process each character exactly once, performing constant time push or pop operations. The combination of constant time operations and linear space makes stacks highly efficient for problems involving sequential, reversible, or nested operations. When to use stacks. Stacks are perfect for problems where you need to track items in a last in, first out order. They're ideal for tasks like validating nested structures, such as parentheses, brackets, or HTML tags, because the most recent opening element must be closed first. Stacks are also used in algorithms like depth-first search, where you explore paths and backtrack, or in expression evaluation, where you process operators and operands in a specific order. You'll encounter stacks in scenarios involving undo functionality, function call management, or any situation where the order of operations needs to be reversed or tracked. Their simplicity and efficiency make them a go-to choice for these problems. Common mistakes to avoid. When working with stacks, watch out for a few common pitfalls. First, Always check if the stack is empty before popping or peeking to avoid errors, like trying to remove an item from an empty stack. In the parentheses problem, checking for an empty stack before popping a closing parenthesis ensures you catch invalid strings like close parenthesis. Second, ensure you're matching items correctly during pop operations. For example, in a problem with multiple types of parentheses, like this string, you must verify that the popped opening parenthesis corresponds to the closing one. Third, be mindful of the stack size. If you push too many items without popping, you might use more memory than necessary, especially in problems with large inputs. In the parentheses problem, the stack size is bounded by the string length, but in other scenarios, monitor memory usage. Finally, don't use a stack when another structure, like a queue, is more appropriate. Stacks are for last in, first out. So if you need first in, first out, consider a different approach. Conclusion: you've now mastered the stack data structure. It's like a stack of plates, where you add and remove items only from the top, following the last in, first out rule. We explored its operations, push, pop, peek, and is empty, and saw how they work in constant time, making stacks highly efficient. The stack's linear space usage and constant time operations make it perfect for problems like parentheses validation. Stacks are a powerful tool for managing data and algorithms, from validating nested structures to handling browser history or function calls. Practice with problems like checking brackets or implementing undo functionality to get comfortable with stacks. The more you use them, the more intuitive they'll become. Thank you for joining me today.